How's it going? Cool. Cool. Do you all have any questions before we get started? Today we're going to cover section 8.2, and then remember, I'm going to do another lecture tomorrow. This is from our other class. It's section 9.2. I'm going to post that as a video for us to watch between now and Monday. But feel free to watch it live if you like. That'll be at 9:30 Thursday morning tomorrow. So feel free to drop by if you don't have another class, but again, you can just watch the recording and I think it'll be fine. I'll also make sure to post the review today. That way we can go over the review on Monday next week. And then we will not have class next Wednesday, so keep that in mind. Next Wednesday would basically be, because it's after our class is afternoon, it won't meet next Wednesday because of the holiday. And then I'll give you Monday after the holiday to take the exam, or take the test 3, and then we'll have one more day after that. So anyway, so section 8.2 is today. Let's look at that. Finals are 3 weeks from today, or from 2 days ago. So roughly 19 days away. What date? Let's see. We got a calendar over here. Let's see, that would make it December 7th, I believe. Now, what's going to happen, I think, is I'm not sure how the testing is going to be done, first of all, whether it's online or in person, or what we've decided as a result of that poll you filled out. So it may be a different day that week, just one that might be more convenient for you, or the week prior even, if you prefer. But we won't review until prior to that. Or if you do it online, then you can do it basically anytime Monday through Wednesday that week. So anyway, something like that. But Yeah, December 7th through 9th, somewhere in that window, I would expect. Now, one thing we have not talked about this semester is proportions. So in section 8.2, we look at the distribution of the sample proportion. So let's talk about what a proportion is. In the statistical sense. So the proportion of a population, this is a fraction of the population that does or does not have a certain characteristic. Just whatever we're interested in at that point. Whether we're meeting one characteristic or another. So we might say the proportion of the population that prefers to wear Velcro in their shoes, which is very young and very old people. The proportion of the population that walks to work, the proportion of the population that does not drink alcohol. So there's different ways we can phrase that, and we can create different proportions based on that. But really, it's just a percentage of the population that meets or does not meet a requirement, like we've just said. Now, we're looking at the distribution of the sample proportion, so let's talk about the sample proportion next. Now, our population proportion, for this one, we use the value P for the population proportion. For the sample proportion, I'm started writing the syllable again. Proportion, we use, this is P, but we put a little hat on it, so it's P hat. P hat is defined as x over n, where n is the sample size, as always. And x is the number that does or does not have a certain characteristic from the sample. Okay. Okay, so calculating the sample proportion is not particularly difficult. Like I said, we just had to have these two numbers. So we might say that, for example, 500 million college students are surveyed. And I don't know where that R came from. Sorry. Um, let's see, and then we'll assume this is like in a normal semester, then whatever it is we have this year. 500 million college students are surveyed, and 37 respond that they take or they use the city bus system to get to the college. Okay, so we could say, okay, what is the sample proportion there? Well, our sample size is 500. We know that's the denominator. And of that group of 500, we had 37 that possess the characteristic that we're interested in, which is the number of, or the proportion of students that use the city bus to get to class. That's 37 out of 500. And we'll use that to go ahead and calculate a proportion, which would be 0.074. Okay. Now, that's just calculating a proportion. That by itself is not difficult, but there's some other things that we'll have to consider as we move forward. Okay. So first thing that we have to consider is what we call our condition for normality. In order for our data to be considered approximately normal, the following must be true. And that is that n times p times 1 minus p must be greater than or equal to 10. Now we look at this value, and if you look at the formula sheets I put into Canvas for Chapter 7, 8, and 9, including the calculator instructions, this is one of the things that I gave you. We have to demonstrate that this is true before we can pursue these proportion problems any further. Now, when we think about it, P is the proportion of the population that are generally regarded to have whatever characteristic we're looking for. But it's a percentage, so it's going to be a number less than 1, and so 1 minus p will also be a number less than 1. So we have two small numbers. That means n is going to have to be a pretty decent size in order for this product to be bigger than 10. Usually n would have to be at least 30 or 35, but depending on the value of p, it might have to be as large as 100. That means we can't have our sample size too small and be able to assume that it's normal. Generally, 30 is going to be about as small as it can be, but it might be that we need closer to 100 to be sure that we have a pretty good degree of normality. Okay. Now, in addition to that, additionally, we have the requirement that the sample size n is no larger than 5% of the population, capital N. That is no larger . So we would say n is less than or equal to 0.05 times capital N. So generally, whenever we work a proportion problem, we'll start off by demonstrating these two details. Now this one essentially says n cannot be too small because it has to be at least approximately normal. This one says n cannot be too large. And it makes it kind of a balancing act that it can't be too small or too large, but it really depends on the population that we're looking at. The reasoning here for this part, that we don't want n to be larger than 5% of the population, is this means that if we were to take a second sample, we could more or less guarantee it would be unique from the first sample, that we wouldn't pick the same individual to be part of both samples, and therefore maintaining the integrity of our statistics. So, if our sample is so large that it is more than 5% of the population that we're looking at, then one, we either collected the data too easily and is not reliable, or two, we spent way too much money getting all these samples when we didn't need that many, and three, it calls into question the validity of the results because it is such a large number. Okay, so we do have to demonstrate that as well. So for Midland, I don't know what our population number is like nowadays. Maybe 120,000, maybe 140,000. We could just split the difference there and maybe call it 130,000 and just proceed with that number. So if Midland has a population, if Midland has a population of 130,000, what's the largest sample we could potentially take from this population? What's the largest sample that we could reasonably take from this population and maintain statistical rigor. Okay, and it basically refers to this equation right here. So our sample size n would have to be less than 0.05 times the population, which is 130,000. And so if we multiply that together, we know that n cannot be larger than 6,500. Okay. Now, as long as we didn't take a sample of 6,500, if that is the population of Midland, 130, then we would be okay in this regard. And more than likely, we could go smaller than that. Even if we just took 500 or 1,000, we would have very good results in general, unless we just did not diversify our survey at all as far as the targets of our survey. But generally speaking, at 500 or 1,000, we should be doing very well. As far as accuracy to the overall population, and so on. So we wouldn't necessarily need to take a sample that large anyway. This rule is more for smaller populations and making sure that we're not choosing an overly large sample. Midland is a large enough population that it's not a concern. Now, Midland College, we only have maybe 6,000 students. 5% of 6,000 is 300, so we would have to be very careful not to take a survey in Midland College of more than 300 students. Because then we run the risk of, if we take a duplicate sample, we may actually have individuals that get surveyed as part of both samples, and again, we want unique samples. Now, that's why we have this requirement. Okay. The other thing that we'll need to find is what's called the standard deviation of the sampling distribution. So, for the sampling distribution of the sample proportion, we use the following. So for mu, we use P, our population proportion, and for sigma, we use sigma P equals the square root of P times 1 minus P divided by N. Okay, so we do have to calculate our standard deviation here, and looking at that, it's kind of similar to what we saw with maybe the binomial distribution. The same terms are there at least, but not in the same order. Might be closer to say it's more like the what we looked at last time with the central limit theorem, and that formula there, probably closer to that. Anyway, we also have the z-score formula. is z equals p hat minus p divided by sigma p. So once again we are calculating z-scores just like in 7.2 and 8.1. So really the procedure from here is the same, because we calculate our z-score, plot it on our graph, shade the appropriate area, and then calculate the area, which is equivalent to the probability. After this, it becomes the same. It's just we have some different things leading up to that part of the problem that we didn't have before when we were working with proportions like we are now. Let's look at page 413, number 18. Now, number 18, according to creditcard.com, 29% of adults do not own a credit card. Alright, so we can go ahead and accept that as our p-value, and we don't want to use a percentage in a formula, so we'll change that to a decimal, 0.29 instead of 29%. Part A of this problem says, suppose a random sample of 500 adults are asked, do you own a credit card? Describe the sampling distribution of p hat, the proportion of adults who do not own a credit card. Now, for this one, what we're really trying to do is a lot of the stuff that we just discussed. We want to check the for normality. Is our sample size large enough so that we can guarantee our data is approximately normal? And we also want to check to make sure our sample size is not too large, so it's not more than 5% of the population that it represents. And finally, we want to go ahead and use this opportunity to find the standard deviation. Okay. So A is basically all of our preliminary work, and the book doesn't really say it that way. I'll be a little bit more clear when I present that to you on both the practice test and the exam. All right. So first of all, we need to show n times p times 1 minus p is greater than or equal to 10. N, we just said, is 500. P is 0.29. 1 minus p, 1 minus 0.29 would be 0.71. Oh no, okay. I had a moment of panic where I thought I used 0.81 for my class yesterday, and no one said anything. But no, I used 0.71. Anyway, so we'll multiply those together. Let me get my calculator here. So we have 500 times 0.29 times 0.71. And so for that I get 102.95. And that is definitely greater than 10. So that part is confirmed. Alright. At the bottom of the page, so I'll flip it over. And the next part that we need to check is that little n is less than or equal to 0.05 times capital N. Now little n in this case is 500. That's our sample size. Now capital N, this is the population that we're studying. So we go back to the question. According to creditcard.com, 29% of adults do not own a credit card. So it sounds like we're looking at adults. Now what's not written here is whether this is all adults in what area. I think we can confidently say that this is referring to adults in the United States. But sometimes the context clues are going to be there. Other times the context clues are going to have to be, they're going to be a little bit more elusive, so we have to work a little harder to figure out what the heck we're looking at. Basically, our population, if we say it's the adults in the United States, we think about how many adults in the United States there are. Our U.S. population is around 300 million, probably a little bit more. And I would guess that at least 3/4 are adults, give or take. So if we did 0.75 times 300 million, which is 8 zeros, we would get, what is that, 225 million. So we're saying we figure there's 225 million adults in the United States, and we want 500 to be less than 0.05 times that. Turns out 0.05, and it's all kind of silly at this point because we can tell it's totally going to be less than. But 0.05 is 11,250,000. Which absolutely checks out. Third part, let's go ahead and find our standard deviation. Standard deviation, which we've denoted sigma sub p. P because it's a standard deviation for a proportion, is the square root of p times 1 minus p over n. Now p is 0.29, 1 minus p is 0.71 still, and n is 500. Alright, so we want the square root. So we have 0.29 times 0.71 and divided by 500. Now, we can do that in one long stream because it's 2 multiplying and the third one dividing. If it had been 1 on top, 2 on bottom, we'd have to be a little more careful about this. But we close parenthesis. And we get 0.02029, so 0.203, I would say. I would round a little bit further here than normal. I would say 4 decimal places like we're doing for the standard deviation specifically, because we're going to use that as part of another calculation. Excuse me. We use that as part of another calculation when we find the z-score and then we approximate the z-score. So we want to make sure we don't over approximate here so we can get a better approximation later. Okay, now we can go to part B. Now this is still on that same problem 18. to the next page. What is the probability that in a random sample of 500 adults, more than 30% do not own a credit card? Okay. So we want the likelihood that more than 30% would not own a credit card in this sample of 500. So that means p hat will be 0.30 to represent this 30%. Now we have everything else already. We know n is 500. We know p is 0.29. And we found sigma p to be 0.0203. So we'll calculate the z-score. And plug in the values that we have. So we do p hat minus p, so 0.30 minus 0.29. The bottom of sigma p, which is 0.0203. So it's 0.01 over 0.0203. Now we want to approximate p. So we divide that out, we get 0.49. Again, z-score we always round to 2 decimal places. Alright. So we go ahead and draw our graph. And 0.049 is a little bit to the right. Which side are we going to shade for this line? I'm going to shade to the left or shade to the right? To the right? Mm-hmm. Yeah, it says more than 30%, so more than means we're going to shade to the right of whatever z-score that we get. Okay, so our lower bound is just 0.49. Our upper bound is 10, just for lack of a number there. So second data. Right to distribution, and I mean normal CDF. Mu is 0, sigma is 1. And then we said 0.49 for our lower bound, and 10 for our upper bound, and then enter. So that gives us 0.3121 after rounding. So it's entirely within the realm of possibility that we could perform this survey of 500 individuals, or a study of 500, more than 500, or 500 individuals, and we'll find that in a population where 29% of adults do not own credit cards, in this sample there's actually more than 30% that do not own credit cards, and that occurs in 31% 31.2% of the samples. I keep pulling down my sleeves because my arms are cold, and I keep pushing the sleeves back up because it bothers me. It's crazy. Alright. So, let's see. I think we saw question C and D here. So let's look at question C. And in 18C we ask, what's the probability in this sample of 500 that between 25% and 30% don't own a credit card? Okay. In this case, they've given us two values to consider, 25% and 30%. It's important that each of those is recognized as a p-hat. And we have to create a z-score for both numbers. So for p-hat equals 0.25, z would be 0.25 minus p, which is 0.29, over a standard deviation, which we found was 0.203. So that'd be negative 0.04 over 0.0203. And for that, we get 1.97, negative 1.97. So that's one z-score. Now for the other one, p equals 30. For that, you'll recall that we already calculated the z-score once. 30 minus 0.29 over 0.0203, and if you remember, that came out to be 0.49 in part B. As we look here, we're actually finding the z-score for p equals 1.30, and we're doing the same thing here. So we don't need to calculate that again if we already had it. But again, we have two p-hats, two z-scores, so we'll plot both of these on our normal curve. And actually, that'll be the lower and the upper, respectively, of our shaded area. So negative 1.7 would be over here, and positive 0.49 somewhere in here. And we shade the area between. There we go. So our lower, negative 1.97, and our upper, 0.49. So we'll go to our calculator now. Second data, distribution, normal CDF, 0, 1, and then our boundary is negative 1.97, and our upper bound is 0.49. Calculate. So we get 0.6635, which is a pretty solid probability. More than 66% of the time, the result of this survey should be between 25 and 30% that do not own a credit card. Okay. So let's keep going. Part D. Would it be unusual in a sample of 500 people that 125 or fewer do not own a credit card? Okay. Now, we notice they've given us this a little bit differently. They haven't exactly given us a percentage, but they've given us the means to calculate it at least. How would we find p hat in this case? Does anyone have an idea? (125 over 500). Remember we said at the beginning p hat is defined by the formula x divided by n, where n is the sample size on the bottom, 500, and x on top is the number of people that meet a certain requirement, which is in this case they don't own a credit card. Now specifically it's 125 people or fewer, which does affect the outcome because we want to shade to a specific side. But yeah, we end up with 125 over 500, and that comes out to be 0.25. Now, for p hat equals 0.25, you'll recall we've already found a z-score. It has a z-score of negative 1.97. Okay, so we already have the z-score. So we'll plot that on our number line, or not our number line, our normal curve, my ever-changing normal curve shape that I draw. Negative 1.97 would be to the left of 0. And it said 125 or fewer, so which side should we shade to the left or to the right? Left, yes. Fewer would mean less than or to the left. Well, sorry, I thought I moved that up far enough, but not quite. There we go. So our lower will use -10, and for our upper bound, we'll use -1.97. Calculate. So 0.0244. Okay. So the question is, would it be would it be unusual for that to occur to get this result? Is that an unusual outcome that we could find 125 people out of 500 that do not own a credit card? Yes, it is unusual. Remember, we defined unusual in a statistical sense in that we have a probability that's less than 5%. This is, well, you get the drift. There we go. Alright. So that takes care of problem 18. Let's also look at number 20 today. '20 is probably a better example of how this question would be presented on the test, because I'm not going to give you a whole lot of extra parts to do. Like, I'm not going to ask you to do each of these problems 5 times or whatever, but I'm going to give you some different scenarios. You're going to do each one once, maybe twice, so something like that. You'll see on the practice test what it'll look like. So let's look at 20. Now 20 says, the Pew Research Center recently reported that 18% of women age 40 to 40 years old have never given birth. Suppose a random sample of 250 adult women age 40 to 44 results in 52 indicating that they've never given birth. Explain why this is not necessarily evidence that the proportion of women in this age range who have never given birth has increased since the time of the study. Now, the wording here is not great. First of all, it actually reads like a problem that we're going to cover in chapter 10, and I wonder if that's was intended here to kind of preview what we're going to do later. But anyway, we want to work this problem like we've been working these other problems, these other parts of this problem. So we know that based on this research center, they've established the probability of women that are in the age 40 to 44 range, 18% have never given birth. So we'll use that as the population proportion. Now, we're also given that we have a sample of 250 women in that age range, and we found that 52 of them have never given birth. So this is the data that is given to us initially. First thing we want to do is check our conditions for approximately normal. We also want to check to make sure the sample size is not too large, and we want to go ahead and find the standard deviation. Those will be the first three things that we do here. So A, we need to show n times p times 1 minus p is greater than or equal to 10. So we have n and p here, 250 and 0.18. 1 minus 0.18, that would be 0.82, greater than or equal to 10. And if we just go ahead and multiply that out, let's see, we have 250 times 0.18 times 0.82, 36.9 there. $36.9 is definitely bigger than 10, so that checks out. Okay, next part we want to demonstrate is that n is less than or equal to 0.05 capital N. Now our sample size n is 250. The question is, how large is our population? Let's look at who we're studying first of all. We're studying women age 40 to 44 years old that have never had children. I believe that we can isolate this to the United States specifically, because it didn't say anything beyond that in the description of the problem. So we already decided in a previous example that the adult population of the U.S. is 225,000. Sorry, 225 million. Okay. That's the number of adults that we have. I feel like we can reasonably say that approximately half of those are women. So we're down to 112,500,000. Now, of those women, how many are in the 40 to 44-year-old age range? Now, this is where prediction gets a little bit dicey, but it's okay. What I decided when I did this problem yesterday, and I think it's not a bad interpretation, is that you think that the average age that Americans live to, and for women it's something like 75, and for men it's a little bit younger, like 72, for various reasons. Anyway, so let's say 75 is the maximum age, or maximum average age for women. So that means we have an 18 to 75 age range. So I took 75 minus 18. Okay, that means we have a 57-year period, and we want a 5-year period out of those 57. So 5 years out of the 57. So we estimate that 8 to 9% of the population of women is between the age 40 to 44, and so I multiply that times our earlier number, 112,500,000, and we ended up with oops, I pressed the wrong number somewhere. I hit it equals twice. That's what I did. So, long story short, it looks like we're at about 9,900,000. Now, it's probably clear to you that this was extreme overkill as far as how we needed to calculate this value. We didn't have to think about it that hard. Even if we just kind of lowballed it and said, okay, you'll need to do something similar. But even if we said, okay, we figure that with 112 million women in the United States, adult women, at least 1 million of them are in the 40 to 44 range, and then this easily works for 1 million, and it certainly works for 9.9 million like I came up with here. So I think the one that I give you, let's see, this came out to be 495,000. Great. So as long as our sample didn't exceed 495,000, we're good. So I feel like we're in a good place. What I may do on the test is go ahead and give you an estimation of the population that we're looking at, so that you don't have to do all that extra work with effort boiling down the population to the one that we're specifically looking at. So anyway, I don't want you to go through all of what I just talked about there. I just wanted to give you some context as far as how we would think about that. Okay, so we have that. Next thing we need is our standard deviation, sigma p. Again, our formula is p times 1 minus p over n, so under square root. So p, in this case, is 0.18. 1 minus p is 0.82. And our sample size is 250. So we would do square root 0.18 times 0.82 divided by 250, and we get the value 0.0243 if we round. We can normally expect the standard deviation to be a relatively small number like this, no matter what the size of p that we're working with. Around the 2 to 4% range is pretty common. So, all right. Next, we need p hat. Now, in the original problem, it said we had a sample of 250 people, and it was found that 52 of those in that age range of women that had never had any children, or had never had given birth. So p hat, remember our calculation is x divided by n, so we'll plug in there 52 for x and 250 for n, and then divide those together. And that gives us 208. So finally, we can find our z-score. Now for our z-score, remember we take p hat first, so 0.208. I thought about approximating this a little bit, like 0.21. It's probably better to leave this a little bit more exact. I think that is exact, 0.208. and we'll be able to approximate z in the next step, and that'll make it a little more accurate as a result. Okay, so we take 0.208 minus 0.18. So it gives us 0.028 over 0.0243. We divide. So that's about 1.15. That's our z value, so go ahead and put that on our graph, or on our bell curve. 1.15 is to the right of 0. And again, to figure out which side we shade on, we have to pay attention to the question, which was what do you want us to show? Explain why this is not necessarily evidence that the proportion has increased since over the years since the study was originally done. So if we want to show that the proportion is not necessarily increased, we're still looking at what's the likelihood of getting this value or higher. So we would shade to the right. Okay. That one's a little less clear why we would shade to the right. So we do have to pay close attention to what the paragraph or sentences are saying. Now from here it's easy. Sorry. So our upper value is 10. So we go to data, distribution, normal CDF, 1.15, and then 10. Those are boundaries, and then calculate. And we get to 0.1251. Okay. So, what does that tell us then? Well, that means for us to do this whole research that we just did, we took a sample of 250 people, 250 women, aged 40 to 44. And it turned out that 52 of these women had never given birth. For this to happen, to get that number of people or more, 52 or more people out of this 250 that had never given birth, there's actually a 12.5% chance of that occurring. Now, the implication that the number of women in that age range that have not given birth is increasing would only be demonstrated if this were an unusual outcome, generally speaking. So if this had been really low probability that this occurred, then that might indicate that things have changed and that the proportion for the population is actually higher than it used to be since the time of this research was done previously. But this is large enough that this result is well within the realm of possibility in the current models, so we shouldn't be challenging the 18% value just yet. Now, This whole type of question is part of what it's kind of an example of what we call hypothesis testing, which we'll cover in chapter 10 after Thanksgiving. And it's a pretty interesting chapter, but there's a lot that goes into it, unfortunately, like we saw in this problem. Anyway, so so our answer here is no. There is not any evidence that this percentage has increased, because this is not an unusual outcome. Okay. For homework on, let's see, this is page 413. Look at 17 and 19. Okay. And as I mentioned before, tomorrow I'll be lecturing the final section of this set of chapters in my 9:30 Thursday morning statistics class. So feel free to come watch the stream live then if you would like to participate and ask questions. Otherwise, I will post the link to the video in Canvas later for you to catch up with it over the weekend. And then on Monday, we're going to review, so I'll make sure I post a copy of the review for those of you that would like to start looking at it. But as you can imagine, it's a lot of the same type of questions that we've been doing already. A lot of these problems where you just calculate z-scores in some different ways. We did z-scores in 3 different formulas, going from section 7.2 to 8.1 and now to 8.2. And we're going to look at something entirely different in 9.2 tomorrow. So there's a lot here, but there's also not a lot of sections. So it's kind of balanced out, I guess. But yeah, that's the plan going forward for the immediate future. So I hope you all have a good rest of the day, and if you don't make it tomorrow, that's fine. It's not a big deal. But I'll make sure I post that link afterwards for everyone to revisit it at their convenience. So have a good weekend, y'all. If you don't come by tomorrow, like I said, I'll be okay with that. But I'll see you Monday otherwise, and y'all have a good day. Bye.